let's look more at this idea of velocity. We've got this curve, and I want to think of this as the motion of some object. A car, a bug, a plane, a particle. It's going to be the motion of some object. It happens to be in the plane because we're just trying to be a little bit less complicated than a fully three-dimensional motion in space, although that's not really that different. And we know that as time goes on, it comes from here, loops around, and goes back out. And at any point in the trajectory, like at one of these crossing points or at one of these vertical points, anywhere, there is going to be some notion of the velocity of that point, of the particle at that point. That's a vector. It's a quantity with magnitude and direction. And what should its components be? So the velocity is a vector that is measuring how far it goes and in what direction as a function of time. And its components are exactly just how much it goes in the x direction as a function of time and how much it goes in the y direction as a function of time. So that x velocity that we've been using in the first video and the y velocity in the second video, as I advertised, are exactly the components of a vector, and those indicate the direction and magnitude of motion at any particular time. In this case, let's get down to cases here. That's 3 minus 3t squared, comma, 6t. And we've seen some particular examples of that. And the main thing that you want to realize, the first thing you want to realize, is that this vector, if you draw that vector, drawn with its base at the point, the appropriate point on the curve for the appropriate t value, will be tangent to the curve. Because if you're going along a curve, say right here, and you draw a vector that's supposed to be the vector of your velocity, that should be in the direction of motion, and that's going to be tangent to the curve. So that's one of the big uses of the velocity vector, is it gives you a vector that's tangent to the curve. Okay, so this is an interesting fact about the direction of the vector. And so we know its components, dx dt and dy dt. That's one description of a vector. But remember, the other description of a vector is magnitude and direction. Well, one thing to get, say, a good pictorial idea of what direction it's going to have is it's going tangent to the curve. Okay, but what about the magnitude of the velocity? We have a word for that. The magnitude of the velocity of anything is the speed. That's how fast it's going, irrespective of direction. So this is something you learn in a pretty basic physics class, that velocity is the magnitude and the direction of your motion, and the speed is just the magnitude, just how fast you're going. Well, guess what? We have a formula for the magnitude of a vector. This comes from pre-calculus. The magnitude of a vector, and the notation for that, people sometimes use single bars or double bars. I'll just use single for now. The magnitude of any vector is going to be just a Pythagoras calculation. You draw that vector as a little arrow in the plane. It goes dx dt to the left or right, dy dt to up and down, and you do Pythagoras on that right triangle, and so you're going to get dx dt squared plus dy dt squared. And that's the speed. So in the specific case, where that vector is dx dt dy dt, that's going to be the speed. Let me make that, yeah. Okay. So that's really cool. So we can ask, what is the speed when, let's say, at that crossing point, at the self-intersection point? How fast is it going? And that's going to be the square root of, so what was dx dt at the crossing point? That was root 3. Dx dt was minus 2. Dy dt was 2. Ooh, just kidding. Just kidding. I think that was after a cancellation. Ha ha ha. Yes. This is a very common mistake. I'm kind of glad I made it. We were looking at dy dt and dx dt, and here's what they really were. And we had a nice little cancellation that happened. And that's fine as long as we only care about the ratio and about what direction we're going in. But if we care about the size, we totally don't want that cancellation. So I was wondering why those 3's had gone away. So dx dt is 3 minus 3t squared. Yeah, here it is. It's right here. Okay. And that was 3 minus 3t squared. Okay. And that was root 3 squared. There we go. Okay. Plus 6 root 3 squared. Okay. So here's the speed. Let me write it out. Okay, whenever I have a vector, I'm trying to make it boldface to emphasize that that is a vector quantity. And then when you put the bars around it, you're just saying, I want just the magnitude of that. Okay, that's going to simplify. This is just minus 6 quantity squared. So let's not even write the minus. Plus, and then this is 36 times 3, 108. That's 36. Ooh, and it's nice. Square root of 144 or 12. So there's a nice number here. This thing is going with speed 12 at that self-intersection point. In general, we can go further than that, and this is what I was almost writing before, but I didn't want to quite get there. We can have the function, the speed, this velocity is a function of time, and so the speed, the magnitude of the velocity, varies with time, and we can just go ahead and write down the full formula. There we go. Plus 6t quantity squared. So that looks a little complicated, but we can just plug in any t we want and get the speed at any particular time. And it turns out that I've picked an example where this actually simplifies quite a bit. And so let's look at that, because that's actually going to be crucial to the next stage. Let's go ahead and multiply that square out. And I have to admit, this is a little bit of a contrived choice here of this example to make this work, but you'll see this a lot in books because the next stage we're going to do, arc length, it sometimes requires this kind of contrived example. Okay, so the cross term is minus 18, 2 times 3 times 3 times t squared, and then plus a 9 t to the 4th. Now I'm going to square that out, 36 t squared. And you might notice something. Oh, when the t squareds collapse together, it happens to be, just the way the numbers work out, that just turns into a plus. And that's a really good thing, because this is a perfect square trinomial. It's exactly the square of what we started with here with a plus instead of a minus. So this is the root of the quantity 3 plus 3t squared. Aha! That is just 3 plus 3t squared. Now, I want to advertise one little tricky thing. Don't always take the square root of a square and assume it's exactly what you started with. In general, it's the absolute value of this quantity. But hey, 3 plus 3t squared happens to already be positive, so you don't need the absolute value. Okay, so that's really nice. So in fact, for this particular curve, chosen pretty specially, the speed actually is a nice simple quadratic function of the time. And it's kind of nice to think about what that says in terms of the picture. When t is either big positive or big negative, this is really fast. It comes in and we get a minimum speed at, ooh, I'm just doing weird things with the formatting, sorry, at t equals 0. And that's where that speed equals, that speed is equal to 3. And so let's go back to the picture. It's telling us it's whizzing in, zoom fast. It goes here with the speed we calculated a minute ago, then comes in, slows down, goes here with a pretty substantial speed here still, 3, and then gets faster and faster and faster and goes out here. And that's a nice thing to be able to say. So in the next video, we will see how knowing the speed, especially as a function of time, is crucial for calculating the length of the curve between any two time values.